talk about some work with Joe Henson at Imperial and Matt Pusey, who's at Perimeter Institute. And I want to present two main results. And the basic idea will be to take the Bell setup that Bob mentioned, which is used to derive non-locality in quantum theory, and change the causal structure and define a framework for exploring non-locality in different causal structures from the usual simple Bell scenario. So that might involve using different numbers of parties or more complicated sequences of measurements. So I'll explain exactly what this diagram is going to mean formally as we go through the talk. So I'll give some background, and then I'll describe the formalism of classical Bayesian networks, which is what we use to build on to get quantum and more general theories. And then I'll describe some applications which will be kind of similar to the way that we understand the Bell scenario, in that quantum non-locality can reach a certain bound, but it won't be able to reach, for example, the maximum non-local bounds that the theory could attain. So as I was saying, the usual Bell scenario is quite a simple setup. We have two parties, and we think of them embedded in, let's say, Minkowski spacetime, and so they have light cones attached to the locations of their measurements. And although this allows us to understand quantum non-locality and derive sort of the fact of non-locality, various lines of research have attempted to modify this basic causal structure and derive more powerful results. For example, Sandra Pescu a while ago had the idea of using sequences of measurements on a system in order to display non-locality of certain mixed states whose non-local statistics wouldn't be obtained just in this simple Bell scenario. And recently, a very interesting result by Gisin's group showed that if you have a hidden variable theory which recovers the statistics of quantum mechanics, then you can't have that theory, you can't define that theory with a finite speed superluminal influence in order to get that non-locality without breaking the causal structure here. In other words, it would contradict the no signaling that we would impose between Alice and Bob and vice versa. And so I mention these results, and in particular the second one, because they use very complicated causal scenarios in order to derive new types of features of our quantum theory. For example, this one has a very intricate quadripartite scenario in which they have complicated relationships to each other. So this is some motivation, and it leads us to the idea of using Bayesian networks, because these are used in machine learning and various other aspects of applied statistics in order to model random variables assigned to different nodes in some causal structure. And it originated in applications of computer science, in particular artificial intelligence, some decades ago. And even in that area, it's concerned something which is very close to non-locality, namely inference from partial observations, meaning we have some nodes in our graph which we have access to, we can observe the probabilities, and a problem that was studied was, for example, causal discovery. So given these correlations, the observed correlations, what causal structure fits the data? So what hidden nodes should we add? And some of the key people in this field have looked at how to give a more abstract notion of independence. And that's quite related to what I'm going to talk about. So for example, Phil David and Stefan Lauritsen tried to provide axioms for causal inference. So moving away from concrete implementations of Bayesian networks. And a group at Carnegie Mellon developed automated causal discovery algorithms. So you supply your program with some probability distribution, and it will supply you the best causal structure that will explain it. And that's very useful things like medical trials where you're trying to understand how effective a particular drug would be. But these are all very interesting aspects of classical Bayesian networks, and what our project here is concerned with is to try and see whether quantum information could be related in an interesting way to these problems. And I think Bob mentioned Judea Pearl also wrote a very influential book which won him both the Lakatos Award and the Turing Award because of the way that it showed that classical Bayesian networks permeate so many aspects of reasoning, scientific reasoning. So what is a classical Bayesian network? Well, it's actually, in the first instance, quite simple. So we just supply a graph, a DAG, directed acyclic graph. We have some nodes, and we assign a probability distribution to that DAG. So, for example, in the Bell scenario, we could write down this DAG, and this would have measurement choices X and outputs A and B, and so that's Alice's side, that's Bob's side, and this is the hidden variable in the past, which will sometimes explain the correlations. And note we start off by defining a joint distribution on all of the nodes. And in order to make sense of causality in this framework, we need to impose some condition on that joint distribution. So the first way we could do this is to require that that joint distribution factors in a certain way according to the structure of that graph. So the way this is usually done is to impose the Markov condition, and we say that the joint distribution is Markov with respect to that DAG if it factors as a product of certain terms, and each of these terms, given the probability of an occurrence of an outcome at a node, and it's conditional only on its parents. So it's independent of everything else in the graph. So another way of saying this is that the probability at that node is independent of all of its non-descendants once you condition on the parents. So I'll give an example in a second which will make it clear. And we define a classical Bayesian network simply by defining a DAG and a particular probability distribution that is Markov with respect to that DAG. And this condition is meant to impose the fact that the probabilities kind of flow along the graph. So the probability distributions, these conditional probability distributions can be multiplied in a way that matches the structure of the graph. So, for example, we can look at the Bell scenario, and if we impose a Markov condition on the joint probability distribution, then this corresponds to factoring it like this. This product of these terms. So this is saying that the probability of the outcome A is independent of B and Y once we condition on its parents, X and lambda, and so on for the other nodes. And actually, this is exactly the same as the locality condition that we usually use when studying non-locality. But in other words, the Markov condition does capture the usual locality condition once you sum over the lambda here. So that's a good sign because it means that we're studying the right thing, and we can apply the Markov condition in more general scenarios now and take that as our notion of locality. And in particular, we can use a notion in classical Bayesian networks which mirrors the idea of hidden variables in quantum non-locality, and that's the idea of latent nodes. So a latent node is just what we would ordinarily call a hidden variable. So it's not some node whose probabilities are not observed, but we add in order to explain some correlation. So that's exactly what we do in the Bell scenario. We observe the correlations X and A, and we hypothesize that there is some hidden variable in the past from which, by summing over, we can obtain the observed correlations. And of course, in quantum locality, that's not possible. We can't just provide a random variable there in order to obtain a correlation. And so that means that we might want to consider a different notion of causality than just the Markov condition. And the second notion that we can consider is what causal statements can we make only about these observable nodes, the white one. So this grey one is the hidden latent node. And the most general kind of statement we would like to make are independencies amongst the nodes. And the most general one is, in fact, conditional independencies. Just as in the Bell scenario, as Bob was explaining, we study, or we impose the fact that due to the background causal structure, there are independencies amongst the observable nodes in the Bell scenario. So that would be the inputs and outputs. And we can write a general statement about conditional dependence like this. This is just standard notation. We use this double upside down turnstile in order to say that x and y are independent once you condition upon z. And so that just means that they factor like this. And as I was saying, this is just a generalization of the conditional instances that we study in the Bell scenario. So, given that we built up this structure, it would be nice to use the graphical form of a DAG in order to calculate these conditional dependencies. And in the classical literature, there's a very standard way of doing this, and I'll try to give an intuition about this graphical condition by describing some examples. So there are two examples which are useful, which we call the fork and the collider. And in the fork, we can see that if we have Markov distribution for this DAG, then the joint probability distribution will satisfy this statement. The x and y will be independent in z. But if we look at the collider, that statement, the independence of x and y in z, will generally fail depending on how z is defined. So for example, if we just define z to be 0 when x equals y, then conditioning upon z will immediately introduce a correlation between x and y. Because once we know that z is 0, we know that x and y are equal. And this shows us that there's an important difference between the graphical structure of forks and colliders, which we can use when defining the graphical condition for deriving independencies. And this graphical condition is known as the deseparation condition. And what it amounts to is just generalizing that observation about the difference between forks and colliders. And we can introduce some terminology of paths being blocked. And that means that if we have a path between two nodes, x and y, we say that it's blocked by a set of nodes. If that path has a middle node from a chain or a fork which is inside Z, or if that path has a collider such that the middle node is not in Z. So that's reflecting the examples I just explained, where we want to exclude the collider, the middle nodes in the collider, and include the middle nodes in a fork.
Also,
Yep.
there can't be a path from M to any node in Z in the second.
Yeah, I think I've actually left that out. And then we just say that some set Z, which is going to be this conditioning set, deseparates x and y if that set Z blocks all the paths from x to y. So it's a sort of bureaucratic condition. It's not conceptually anything more interesting than what I just described as the difference between forks and colliders, but you need to include all the paths. So here's about an example that we can use to orient ourselves. So we write down the the Bell DAG, and we can look at the paths between A and Y. And we see that there's only one path, this one. And this path P has a collider at B, Bob's output. But that middle node in that collider is not in the node X. And so, hence we see that X blocks the path between A and Y. And if that deseparation condition is a good criterion for deriving the independence, then we should have that the probability of A is independent of Y given X, which we wrote down as this double turnstile, and that's the case. And so now we have these two different conditions. We have the graphical condition, which we write down with this single upside down turnstile, and the probabilistic independence condition, which we have written with this double upside down turnstile. And we want to know that this graphical condition is a guide to deriving the probabilistic conditions. And that's what exists in the classical case, meaning that the separation criterion is soundly complete for deriving the conditional dependencies in the DAG. Meaning that if we're looking at probability distributions which are Markov with respect to the DAG, then if the deseparation condition holds, then any probability distribution defined on the nodes of the graph, which is Markov with respect to that graph, will satisfy the formally analogous probabilistic independence condition. So in other words, we can use the graphical conditions to derive the no-sigma conditions in our graph. And conversely, it's complete, meaning that if the graphical condition fails, then we can find a probability distribution assigned to the DAG for which the independent condition won't hold. So the point is that it characterizes the independent system graph. We can just use the graphical condition. And I want to explain how that tool can also be used in more general theories, not just classical probability theory. So what that means is that we want to introduce nodes which are non-classical here. So before, in the Bell scenario, we were just considering having a classical random variable in the past of Alice and Bob's output. But we want to define something which could be, for example, some quantum resource or some general non-local resource, which will generalize the idea of classical Bayesian network and allow us to import all these tools. We have to have some idea of what this means formally. And to do that, we build upon some work by this idea group that Bob mentioned, who introduced a framework, a graphical framework for defining generalized probabilistic theories, so arbitrary non-local theories on circuits. We're going to graft on these classical nodes. And that will be a kind of hybrid between classical Bayesian networks and this circuit framework. So I'll just sketch how that's done. And it basically involves three ingredients. So we have some systems, we have some so-called tests between these systems, which are just uses of some physical device, like an external act device. And we have rules about defining these tests. So for example, we can use a graphical calculus that basically the same one that Bob just described. And this could be some tests, and with input and output systems A and B. And these tests always have classical random variables attached. So these are, for example, representing probability preparing this particular state row. And we can combine these tests in sequence and in parallel. And the way that we obtain some framework for looking at arbitrary non-local theories is by requiring that the closed circuits yield probability distributions on the classical random variables attached to these tests. And I don't really have time to go through the details, but let me just say that we should think of the edges as having, for example, in the quantum case, a Hilbert space attached to them, and density matrix for the state. But one can define other types of theory which have different geometries than just the geometry of definition operators that you get from quantum theory. And these will yield other theories which have different types of non-locality as compared to quantum mechanics. And one can also include classical probability theory here by the appropriate definition of those circuits. So actually this is just describing what I just said, that we will have observed nodes which will be the classical triangles which will represent classical probabilities, and the unobserved will be those circular nodes which will represent these non-local resources that we can use to characterize different types of theories assigned to this Bayesian network. And these different tests will, for example, correspond to a different shared resource that can be used in the Bell scenario. So bottom line is that the observed nodes are the classical part of the network where measurements are occurring, and the unobserved nodes are the non-local part, which are yielding the observed correlations. And that means that in this diagram, we should think of the edges between the observed classical nodes as different in character from the edges between a circular node and a triangular node. Because here there's a system undergoing a measurement, and A will represent the probability of that outcome. But here there will be just conditional dependence, as we have in the case of the classical Bayesian network. And the meat of a classical Bayesian network is the Markov condition. And we need an analog of that because now we're generalizing from classical probability distributions. And the analog will be this generalized Markov condition. And what that means is when we draw this sort of diagram with this sort of mixed DAG with observed nodes and unobserved nodes, then that should be interpreted as one of these type of circuits, meaning that there will be some state preparation, some transformation, and some measurement here. These probabilities will be the same as the observed probabilities here. So this type of circuit framework is very general, and so we call it generalized Bayesian network. And it's, as in the classical case, it's a pair consisting of some classical probability distribution and some DAG, such that now this probability distribution obeys a generalized Markov condition with respect to this graph. So, question is, what formal properties do these generalized Bayesian networks have? And I was explaining this deseparation condition and how we can use it to characterize the conditional dependencies of the observed nodes in your DAG. And we would like to know whether that still holds. And in fact, it does. And an exactly analogous statement holds. What we have to do is just replace the idea of a classical Bayesian network with a generalized Bayesian network, and replace the classical Markov condition with our generalized Markov condition, and we can derive exactly the same soundness and completeness of the deseparation criterion for these generalized Bayesian networks. So that means that we've defined the notion of causality, let's say causality here, meaning that, for example, in the Bell scenario, we can think of this circular node as the cause of these correlations. And we can also define more complicated scenarios. And in that situation, it doesn't matter what resource we would use here, the theory will still obey all of the observable conditional independencies as if we were to have classical random variables here. So that's the sense in which we obtain limits on the correlations from our framework. And correlations we observe here. So even though we can't explain non-local correlations if we use a triangle here, we can explain them using more general shared resources shared between Alice and Bob. So I should probably stop there.
Very good. Any questions? Yes.
Just one, so it's sometimes said that that Reichenbach's common cause principle fails for quantum mechanics. I mean, there's a fair bit of debate about whether it does or doesn't in like philosophical literature. The idea being that in quantum mechanics, the measurement outputs in the Bell scenario don't factorize given the preparation of some entangled pure state. But given that in your formalism d-separation is upheld, does that mean the status of the common cause principle is also upheld?
In a certain sense, it's a kind of weaker notion of it. What will fail will be the fact that one can obtain the observed correlations by summing over some classical invariable. But that equation will have to just be replaced by computing the correlations with that circuit.
So one could probably just write down a slightly modified statement of the common cause principle just to specify, say, observed variables for the factorization, and then that would still hold.
Yeah, I think it would need a lot of